The redirect from HTTP to HTTPS is a crucial step in any HTTPS deployment. During this redirect, the browser is told to load the HTTPS version of the application. Once the redirect to HTTPS has happened, the communication channel is secure. Unfortunately, the redirect itself remains vulnerable to network-based attacks. By executing an SSL stripping attack, the attacker can get a man-in-the-middle position. In such an attack, the attacker intercepts the HTTP request and prevents the redirect from happening. Instead, the attacker fetches the HTTPS page and serves it over HTTP. Let's see how this works in practice. Here, the user visits the BeerSafe application by typing beersafe.eu in the address bar. The browser transforms this domain name into an HTTP request and sends it to the server. The attacker on the network intercepts this request and forwards it to the web server. The server responds with a redirect towards the HTTPS version of the application. The attacker does not forward this redirect, but follows it himself. He fetches the contents of the requested page from the web server. The next step of the attack involves rewriting all URLs in the page. The attacker replaces all occurrences of HTTPS with HTTP. The rewritten page is served to the user's browser as a response to the initial HTTP request. From this point forward, the attacker has a full man-in-the-middle position. The only way to stop SSL stripping attacks is by deploying additional security policies. All modern browsers support the HTTP Strict Transport Security Policy, also known as HSTS. With HSTS, a web application instructs the browser to use HTTPS by default for a specified period. For example, when a user types beersafe.eu in the address bar, the browser will use HTTPS for the first request. Even better, every HTTP URI pointing to the beersafe.eu domain will be transformed to an HTTPS URI. The server can configure an HSTS policy by sending a response header. The name of the header is Strict Transport Security, and it supports two configuration parameters. The first parameter, max age, is mandatory and specifies the lifetime of the policy in seconds. The example shown here instructs the browser to use HTTPS for beersafe.eu for 1 year. Note that the period is extended every time the browser sees this HSTS response header. A year? Isn't that way too long? Sure, but since we never want to serve an HTTP version of the application, this does not matter. As a rule of thumb, the time between two subsequent visits from one user determines a sensible policy lifetime for an application. If your users regularly visit your application, a lifetime of a couple of weeks would already suffice. Of course, setting a longer lifetime is not a bad idea. But if your users visit your application once a year, for example during tax season, a lifetime of 1 year may even be too short. The second parameter of an HSTS policy is the optional Include Subdomains flag. This flag instructs the browser to apply the HSTS policy to all subdomains of the domain that sets the policy. In our example, we set the policy from beersafe.eu, meaning that the policy also applies to www.beersafe.eu. Note that the Include Subdomains flag can be dangerous. It prevents the browser from making HTTP requests to all subdomains. If a legacy HTTP service is still running somewhere, it will become unavailable to all browsers that have seen the HSTS policy. Let's see HSTS in action on our training application. The web server will send the HSTS policy you can see here. When we visit the application in our browser, we can see the policy as part of the response. From now on, the browser will always use HTTPS for requests going to beersafe.eu. Even if we explicitly navigate to an HTTP URL, the browser will send the request over HTTPS. Once enabled, the security benefits of HSTS are enormous. But what happens the very first time the user visits our application? How can we protect the user then? Look at what happens when Chrome has not yet seen our HSTS policy. The first request is still sent over HTTP, because this is the default browser behavior. Chrome will only start enforcing the HSTS policy after it has followed the redirect and received the first HTTPS response. This means that if we visit an application for the first time over an insecure network, we are still vulnerable to an SSL stripping attack. This is a trust on first use problem. Such scenarios exist with other security measures as well. The only solution is to inform the browser upfront that the application wants to use HTTPS. For HSTS, browsers support a preload list of sites that want this type of behavior. Adding your site to the list of HSTS preloaded domains means opting into the mandatory use of HTTPS for all requests, even the very first one. Before you can add yourself to the list, you need to meet several requirements. First, you need to add the preload flag to show your consent of being added to the list. Second, you need to have the include subdomains flag enabled for your entire domain. Third, you need to have a sensible HSTS configuration. You can find the full list of requirements and the submission form at hstspreload.org. A final word about HSTS. If you want to disable your current policy, the max age needs to be set to 0. Omitting the header from the response is insufficient to disable the policy. To conclude, deploying your application over HTTPS is only step 1. Due to attacks like SSL stripping, an attacker can still become a man in the middle. To prevent this, you need to deploy HTTP Strict Transport Security, or HSTS. HSTS tells the browser to use HTTPS by default, thereby eliminating the attack vector for SSL stripping attacks.